Okay, so welcome back. And before we get into the examples, let's introduce some other terminology, some other concepts that we're going to run into. Okay, so as I said before, a sequence can be represented as a function, right, over the positive integers. So we can represent a sequence of numbers, right, as a function of n, where n takes on integer values, positive integer values. Okay, so in this case, since we can represent it as a function, a discrete function, right, where it's the domain of the function is the positive integers, right, then it makes sense that we can graph these. And so if we look at the sequence that we saw before, right, so we could say a sub n equals what? 2 to the n. Where, or actually, hold on. 2 to the n for n greater than or equal to 1. And we could say a sub 1, so this would be yeah, I think that's it. Yeah. 2 to the n for n greater than or equal to 1. Okay? So we can represent a function, and so here's a graph of the function. So each dot represents, so for example, this is 1, 2, 2, 4, 3, 8, and then way up here is 4, 16. Okay? So this graph here represents the sequence 2 to the n for n greater than or equal to 1. Okay? So now, this is going to be important graphically later as far as understanding when we get to divergence and convergence and when we start talking about limits, okay, of sequences. But before we do that, let's talk about two different very common sequences that you're going to want to know and understand. And you probably remember things like this from years ago in math. But an arithmetic sequence. What is an arithmetic sequence? It's a very common sequence, and it's one of the big characteristics of an arithmetic sequence is that there's a common difference between terms. Okay, so you start with a first term, right? And then what you have is you have a common difference or something that you're adding or subtracting from the previous term, right? So if you take any two consecutive terms, and you subtract them, you're going to get the same difference. That's where the common difference comes from. So an arithmetic sequence is a sequence of numbers where if you take any two consecutive integers and you subtract them, you'll get the same number. Okay, that's the common difference. So you'll start with a first term. That first term is explicitly given, and then from there you can get your common difference to get the rest of the terms. So if I say, 1, 3, 5, 7, 9, then in that case the first term is 1, right? You have your starting point, and then the common difference is 2. So that's going to represent an arithmetic sequence. Okay, so that's 1. Now, the other type of sequence is called a geometric sequence. And a geometric sequence, instead of having a common difference between consecutive terms, we have what's called a common ratio. So what happens is if you take any two consecutive terms within the sequence and you divide them, okay, you're going to get the same ratio. Okay? And so if there's a common ratio, then you have a geometric sequence. So you're going to have, obviously you're going to usually have your starting term, which is going to be given, and then you have your common ratio that defines all the subsequent terms. Okay, and so these are the two common sequences that we're going to study and that will come up from time to time that you're going to want to recognize. Okay, so let's do some examples of what an arithmetic sequence, and I gave you one example, but let's look at another example of some. So if I give you this one, okay, so we start with this here, we give this sequence here. Okay, and so if we look at this sequence, well, the first sequence is 3, right? And then what happens here? If we take the difference between these two, oh, hold on a second, is that the one I want to start with? Oops, wrote down this one wrong. Yeah, there we go. Okay, so this is correct. So now if I start with this again, the first one is 3. So a sub 1 is equal to 3. And then what's going on here? So if I take if I subtract these two, 7 minus 3, I get 4. If I take 11 minus 7, I get 4. 15 minus 11, 4. 19 minus 15, 4. So again, if this continues in like fashion, right, then I can define a sub n equal to what? Recursively, right? So let's just do it this way. So then a sub 2 is going to be what? 3 plus 4. And then a sub 3 equals 3 plus 4 plus 4, right? And so this here just equals 2 times 4, right? Which equals 11. And then a sub 4 equals 3 plus, well, now I got 4 plus 4 plus 4. So that's going to be 3 times 4, okay, which equals 15. And then, so if this keeps going, then look what's going on. How many, I've got a multiple 3 here. 3 times 4, 2 times 4, 1 times 4. So the number of 4s that I'm adding is 1 less than the index. So then I can write a sub n as 3 plus what? Four times n minus 1. Okay, so I've got my starting term, or if you want to just a sub 1, right, plus 4 times n minus 1. So in this case, it's given to us as 3. Okay. Okay. So recursively, right? So recursively, what do we got? This is 3 times what? Plus 4, right? Or if we write this as a sub 1, okay? Okay, now we can write it as an explicit formula, right? So this would be an explicit formula. And so we would simplify this, so we would write a sub n equals what? Well, if we distribute the 4, we get minus 4, so what we would get is -1 plus well, let's rewrite this. It would be 4n minus 1. Right, so there we have an explicit formula. So now, the explicit formula of an arithmetic sequence has this form. Okay, so all arithmetic sequences will have a form of a sub n equals some multiple n plus b, some kinds where c and b are these constants. Okay, so always have the form. Now, if we want to define it recursively, then we could define this one as follows, which I kind of already did, but let's define this recursively. So if we define this recursively, then the way we would define a sub n, the relation would be a sub 1 equals 3, and then a sub n equals what? A sub n minus 1, what? Plus 4, right? So notice that if I want to define this recursively, I have 3, and then guess what? This is going to be a sub 2 is equal to a sub 1 plus 4, which equals 7. And then I can define a sub 3. Well, if I put these two together, right, this gives me a sub 2. And then I just have to add 4. And then for a sub 4, all I have to do is just take a sub 3 and add 4. Okay, and so if we want to define this sequence recursively, this is it. If we want to define this sequence with an explicit formula, here it is right here. Okay. Now, geometric sequences. Well, let's start with another example. Okay, so let's start with this one. Okay, so now, what's the given term? So a sub 1 is 2. And so what happens here when we divide each subsequent number? So 2/3 divided by 2 gives us a negative 1/3. 2/9 divided by a negative 2/3 gives us a negative 1/3. Negative 2/27 divided by 2/9 will give us again a negative 1/3. And again, if we divide these two, we get a negative 1/3. So the common ratio in this case is negative 1/3. Okay, so now we've got the things that we can define this by. So we can define this recursively as follows. Okay, so let's start by listing what some of these are. So we got A, now again, so this means, what is this? This is a sub 2, so how do we define a sub 2? So a sub 2 is what? Oh, it's 2 times negative 1/3, right? And then A3 is equal to what? Well, this is going to be 2, right? And then 2 times 1/9. Well, what's 1/9? That's negative 1/3 times negative 1/3, right? Which is equal to 2 times negative 1 squared. Okay, so let's do one more. A to the 4th. Well, that's negative 2/27, right? But we can pull the 2 out and we get negative 1/27, which is the same as negative 1/3 times negative 1/3 times negative 1/3, which then we can write this as equal to 2 times negative 1/3 cubed. Okay, so recursively, we can define this as what? Well, this right here, again, look at this term here. These two factors give me A2. Right? And this is A1. This 2 here is A1. So I can write this as A1 times negative 1/3. This here represents A2. So I can take this as A2 times negative 1/3. And then, of course, down here, I can take these three factors. This gives me A sub 3, right? And so what do I get? I can define this recursively by saying, hey, A1 is equal to 2. And then what? A sub n equals what? A sub n minus 1 times negative 1/3 for n greater than or equal to 2. Okay, and that's defined recursively. Okay, how can we define this with an explicit formula? Well, again, we go back to the pattern and we see that, well, what's going on here? We've got 2 here, and then we've got 2 times negative 1/3, and then we've got 2 times negative 1/3 squared, and then a to the a sub 4 is 2 times negative 1/3 to the 3rd. Well, if we notice that, well, we can rewrite this A1 as 2 times negative 1/3 to the 0 power, right? Because negative 1/3 to the 0 power is just 1, and 2 times 1 is 2, so we still get the same thing. So we can define this sequence with an explicit formula of n. Okay? So this would be what? 2 times negative 1/3 to the n minus 1 power for n greater than or equal to 1. And so that would be the explicit formula for this sequence. Okay, now, in general, geometric sequences are going to be of the type a sub n equals a sub 1 times r to the nth power Okay, so in general, they're going to have that form. Oh, sorry, I forgot. Not a sub 1. C, because it could be any constants. Okay, so any geometric sequence is going to have that form. Okay, so again, something to recognize, right? So when you're dealing with sequences, you'll be able to pick, hey, is this an arithmetic sequence or a geometric sequence? Where you can see it if, you know, again, if you look at, if you're given an explicit function, right? A function that has the domain of the all positive integers, then you could look at the function and decide, is this an arithmetic sequence or a geometric sequence or neither? Okay? Okay, so see you next time and we'll do some examples.